Hello, am I audible? Hello.
Yes, sir.
Okay, so let us start the lecture. Is the screen visible? ये white screen दिख रही है सबको?
Yes, sir.
Uh, I think we were discussing free semigroups in the last lecture that we. So we discussed the free semigroups. Free semigroups we discussed. Free semigroups we discussed free semigroups. And we have actually so so based on the idea of free semigroups, we have now the idea of this semigroup presentations. Semigroup presentations. Semigroup presentations. So suppose you have a semigroup. So let S be a semigroup. S be a semigroup. We have proven a result while discussing these free semigroups. So we have proven a theorem. One of the theorem says that. So by theorem, so one of the theorems says that there exists a surjective morphism. There exists a surjective morphism there exists a surjective morphism which I denote by psi or psi plus. It is from A plus to S where A is some alphabet and A plus is actually the word semigroup where A plus is the semigroup of all words. So it's a word semigroup. And also one of the theorem says that one of the previous theorem that we have proven, it also says that this S is isomorphic to A plus our kernel of this psi plus. Or in other words, you can say that every semigroup is isomorphic to the quotient of a word semigroup or a free semigroup, because this we have proven that a semigroup is free if and only if it is isomorphic to this word semigroup. So that is to say that every semigroup S is isomorphic to the quotient of the free semigroup A plus by a congruence by kernel of psi plus by a congruence. This we know from our previous discussions. Now, what do we do here in case of semigroup presentations? We just reverse the situation. So we start with an alphabet and we take the word semigroup A plus and take some congruence and take the quotient semigroup and see which semigroups are actually isomorphic to this. So if we reverse, so so in semigroup presentation, we reverse this situation. In semigroup presentations, we reverse the situation. We reverse the situation. Means we actually turn it around. So instead of starting with the semigroup and knowing that it is a quotient of a free semigroup, so instead of starting with the semigroup, with a semigroup and knowing that it is the quotient of a free semigroup and knowing that it is the quotient of a free semigroup, we start with so we start with the free semigroup. We specify a free semigroup we start with this a free semigroup A plus and a congruence sigma, a congruence sigma on A plus, and so define the corresponding quotient semigroup and define the corresponding quotient semigroup A plus our row A plus over sigma, sorry. Okay, and see which semigroups as they are isomorphic to this, and see which semigroup S is isomorphic to this A plus over sigma. So we just go other way around. As I said in the beginning that our previous results, they say that suppose you have a semigroup S, then it is isomorphic to A plus over some congruence. This we have seen in case of free semigroups. But what do we do here? We reverse the situation. Instead of starting with the semigroup and knowing that it is a quotient of a free semigroup, that is, it is isomorphic to the quotient of A plus by congruence, we start with we start with A plus, take some congruence on A plus, construct the quotient semigroup A plus over sigma, and see what semigroups S they are actually isomorphic to A plus over sigma. Okay, so this is actually the idea behind semigroup presentations. Okay, so let me just formally define what is a semigroup presentation. So a semigroup presentation, a semigroup presentation is a pair, so it's actually a pair A, and you have this row, and we denote it in by this symbol SGA row. So it's a pair. Pair means we have two things. We have A and we have this row, where A is an alphabet and row is a binary relation on A plus, where A is an alphabet and this row is a binary relation. Row is a binary relation on A plus. Okay. The elements of A, they are called generating symbols, and the elements of row are called defining relations. So the elements of A are called generating symbols, and elements of row are called defining relations. Okay, and we say that the present a semigroup, we say that a semigroup as a semigroup S is presented by this presentation if S is isomorphic to if S is isomorphic to this A plus our rho sharp. Okay, so this is what I said. We start with A and a binary relation rho on A, rho on A plus, and we say that this presentation it defines the semigroup S or presents the semigroup S if S is isomorphic to A plus our rho sharp. We know this rho sharp. Rho sharp is actually the congruence generated by rho. Okay. so so we have this. So we have this now. This S is isomorphic to A plus our rho sharp. Once this S is isomorphic to A plus our rho sharp, so there is a one-to-one correspondence between the elements of S and the rho sharp classes. So there is a one-to-one correspondence between elements of S and rho sharp classes. So we can think of so we can think of a word so we can think of a word W in A plus as a representative. So as representing the element of S, the element of S corresponding to the class W rho sharp. Okay, because for every element of S you have a unique representative here, unique equivalence class. You can identify elements of S with rho sharp classes here. So any word W in A plus can be thought of as a representative of the element of S corresponding to this class W rho sharp. Now this is actually the definition of this semigroup presentation. Now suppose you have U and V, they are words in A plus, they represent the same element of S. They represent the same element of S. That is to say that their classes are same. So you have this U rho sharp is same as V rho sharp. Then we say that U and V they are equal in S. We say that U and V are equal in S, and we write it as U equal in S V. This is the symbol for this equality. Now, so let T be a semigroup. T be a semigroup, and suppose you have phi from A to T be a mapping, be a map, be a map such that its image A phi, its image A phi, which is a subset of T, A phi, which is a subset of T, it generates T, generates T, then such a map phi is called an assignment of generators. Such a map phi is called assignment of generators. Assignment of, because T is assigned, this semigroup tree, it is assigned generators via this map phi. So this A phi, which is a subset of T, it generates T as a as a semigroup. So we say that this map phi is actually an assignment of generators. Moreover, the semigroup T satisfies satisfies defining relations, defining relations defining relation u v belonging to rho. We say that this T satisfies this satisfies the defining relation u v belonging to rho with respect to an assignment of generators, with respect to an assignment of generators, assignment of generators phi from A to T if u phi plus is same as v phi plus. Now see the situation here. You have the set A and you have the mapping A to A plus, you have the inclusion, and you have here you have here phi, and this is your T. By definition of free semigroup, this words free, because it's a free semigroup, so this phi can be extended to a surjective map homomorphism phi plus from A plus to T by free semigroup criteria. So suppose what I'm saying is that suppose you have a semigroup T and you have an assignment of generators, that is a map phi from A plus to T, and you take any two elements in the relation rho u comma v in rho, where rho is a binary relation on A plus. So you say that this semigroup T satisfies the defining relation, this relation with respect to assignment of generators, this map phi, if you have u phi plus is same as v phi plus, means these images they should be same in T. Okay. So these were some of the definitions. One fact which which is straightforward, which follows from these definitions, is that T satisfies all defining relations in row, all defining relations in row with respect to this assignment of generators with respect to phi from A to T if and only if this row is contained in kernel of psi plus or phi plus kernel of phi plus. T satisfies all defining relation means what? For every uv in row, u phi plus is same as v phi plus. This is the meaning of this. T satisfies all defining relations in row means whatever pair I take in whatever u comma v I take in this row, u phi plus is same as v phi plus. And the fact says that this happens if and only if this row is contained in kernel of phi plus. I think it is straightforward by the definition itself, but I can just explain it for you. So let T satisfies all the, let T satisfies all defining relations in row. All defining relations in row with respect to phi from A to T. Okay. So this means what? This means for all u comma v in row, u comma v in row, u phi plus is same as v phi plus. And if you see the, so this means for all u v in row, this pair uv belongs to kernel of phi plus, or you can say that this implies that row is a subset of kernel of phi plus. And conversely, if row is contained in kernel of phi plus, then for all uv in row implies u phi plus is v phi plus. It means T satisfies all the defining relations with respect to phi. So T satisfies all the defining relations with respect to phi from A to T. This was the small observation. So we have 10 minutes left for this meeting to end, but you will rejoin. We also have one remark. Let S be any semigroup. Let S be any semigroup, and it is defined by the presentation defined by the presentation. Say this presentation SG A row. This means, by definition of the presentation, this means that S is isomorphic to A plus our rho sharp. Now let you take the natural map. Let rho sharp natural. It is from actually A plus to the quotient semigroup A plus by rho sharp. Now I will draw the diagram. So you have A here, you have A plus, here you have A plus our rho sharp. Okay, so this map is actually rho sharp natural. You raised rho sharp natural. And this is what this map here from here to here is what rho sharp natural restricted on A. Rho sharp natural, it is restricted on A. So in other words, you can say that this map is nothing but this rho sharp natural is nothing but rho sharp natural restricted on A plus, because this is what our notation is. हमारी नोटेशन यही है कि अगर आपके पास फाई यहाँ से यहाँ मैप है तो यहाँ से यहाँ एक यूनिक एक्सटेंशन मिलता है इसका. So this actually this is the unique extension of this map. So it's actually the natural map which is the unique extension. What we say here is that we claim that this A plus rho sharp satisfies all the defining relations in rho. Satisfies all the defining relations in rho with respect to the assignment of generators. Here the assignment of generators is this map with respect to with respect to assignment of generators with respect to assignment of generators this map rho sharp natural restricted on A. It is from A to A plus our rho sharp. It is obvious because if you take any because if I take any UV in rho, because for any UV in rho is contained in rho sharp, we know this. So this means this this UV belongs to rho sharp, or in other words you can say that U rho sharp is same as V rho sharp, but this is nothing but U rho sharp natural. U rho sharp natural, its image is same as V rho sharp natural. Okay, or you can say that because these maps are same, so you can also say that this means you have this U rho sharp natural restricted on A plus is same as V rho sharp natural restricted on A plus. So you can say that this row is contained in the kernel of this map, and converse is also true. So by previous remark, you have this. So this is very important remark as far as our semi-group representations are concerned, because suppose you have a semi-group S which has the presentation a comma a row, then this a plus our row sharp, it satisfies all the defining relations in row with respect to this assignment of generator, this map. So now we have a proposition. So we have a proposition. Suppose you have a semi group, so let T be a semi group, and suppose T T satisfies all the defining relations in row, satisfies the defining relations in row with respect to assignment of generators phi from A to T, then T is a homomorphic image of the semigroup presented by, then T is the homomorphic image. T is a homomorphic image of the semigroup presented by the presentation. What does it mean? It means that it means that there must be an onto homomorphism from, that is because if S is a semigroup presented by this presentation, then S is by our definition, S is isomorphic to A plus our row sharp. So there should be an theorem says that T is the homomorphic image of this. This means that you must have a onto homomorphism from say psi from A plus our row sharp to T onto. This is what we claim in this theorem. Okay, so let us see.